Hello students, in the last video uh, I have explained the X-rays, nature of X-rays, production of X-rays and the types of X-rays. So we have seen that there are two types of X-rays, continuous X-rays and characteristic X-ray. In the last video I have explained how the continuous X-ray spectra is originated. That means the reason for origin of the continuous X-ray spectra. And we have seen some of the important characteristics of the X-ray spectra. Then we have seen what is Duane and Bohrs Law. So all these things we have studied about the X-rays. Now today in this video, I'm going to discuss about the characteristic X-ray spectra. So the characteristic X-rays, you know that they are highly monochromatic. So on the background of continuous X-rays, very high intensity peaks of X-rays are observed, and these are nothing but the characteristic X-rays. So the sharp peaks which are observed, they are actually a characteristic of that particular element, and they are highly monochromatic and they are independent of the applied voltage. So the target material, for any target material or for every target material, it has its own set of characteristic X-ray. So you can use this characteristic X-ray as a tool for identifying the elements. So the target elements, each particular target element can give a fixed set of characteristic X-rays. Now the intensity of these characteristic X-ray lines, it is very high, and it is almost 10 raised to 4 times of the continuous X-ray spectrum. Now let us see how these characteristic X-rays are produced. That means the theoretical reason we just try to understand from this diagram here how characteristic X-rays are produced. Okay, so in X-ray tube, last time we have studied the function of X-ray tube, how it works and how X-rays are produced. So in X-ray tube, when the highly energetic electron is bombarded on the target element, suppose this is the atom of the target element. So the highly energetic electron, this is the electron, when it strikes the atom, target atom, it penetrates deep into the atom, and if the energy is sufficient of this electron, it can even go to the very inner shell, that means K shell of this particular target atom. And if it strike the electron here in the inner shell, that electron will be freed from its position. Okay, so it will leave from its position. So in the second diagram, it is shown here. So the electron in the first shell, that means K shell, now it is displaced because of the collision of this electron with this electron, or because of the energy of this electron striking to this K shell electron, it is now made free. So the incident electron energy is sufficient or greater than what is called as the binding energy of this electron in K shell. Therefore, it is now made free from its position. Now what happens? There is a vacancy in the K shell of this target material. So definitely there will be a rearrangement of electron, and the stable position for the electron will be the inner shell. If there is a vacancy, the inner shell is the most stable shell. So what happens here? The electron from outer shell, it will occupy this position, and whatever the difference in energy, that will be given out in the form of a photon. So you can see here, for example, here the outer shell, L shell, suppose this electron, this one, now this electron has perform a transition here from L shell to K shell to occupy this vacant position, okay, which was earlier made available because of this external electron, highly energetic electron striking the target atom. Okay, so because of this transition from L shell to K shell, now the difference in energy of this electron between the two shells of this particular target atom, that will be given out in the form of a photon, and this is nothing but a X-ray photon. Okay, having energy, that is the difference between these two energy levels. So you can specify this frequency or energy of this photon given out in this process as Ek minus El, that is equal to h nu. So this is the photon of energy h nu. E is equal to h nu, you know that. So this is the difference between the two energies. Ek is the energy of this particular level, inner shell, and the El is the energy of the outer shell. So the difference is given out in the form of this photon. So from this equation you can write the equation for frequency of the photon nu. So by just taking this h in the the left hand side, so this nu is equal to h uh, nu is equal to Ek minus El upon h, Ek minus El upon h. So that is what the frequency of the photon given out. That is the frequency of the photon given out. Now remember here, the actual photons given out, they are actually named from which particular shell they are originated. From which particular shell they are originated. For example, in this particular diagram, we have seen that the electron from K shell, it is made free, okay, and the electron from L shell has taken or occupied this position, and the photon is given out. So that means here, because of displacement of the electron from K shell, this characteristic X-ray photon has been originated. Therefore, it is named as a K series X-ray. It is named as a K series X-ray. Suppose now if you assume that the electron has not sufficient energy to reach up to K shell, and it strikes to the electron in L shell. This electron, suppose it strikes to the electron in the L shell, and this electron is made free. Okay. Now what will happen? The outer shell, that means suppose M shell. So the electron from M shell can occupy this position. So at that particular time, you can say that since this electron from L shell is displayed, so that will be a L series X-ray. So that is how you can specify an X-ray, either K series, L series, M series, N series, so on. X-ray depending upon from which particular shell the electron has been displayed. So accordingly, this nomenclature is used: K series X-rays, L series X-rays, and M series X-rays. Okay, now in each particular series, further there are the characteristic X-ray nomenclature. For example, K alpha X-ray, K beta X-ray, K gamma X-ray. So let us see now how these names are given. Which particular X-ray is K alpha, which is K beta, which is K gamma. Let us see here. So for example, this is the typical example we are going to consider. So in this example, the inner shell electron, that means from K shell, is made free because of the highly energetic electron striking on this target atom. So this electron is from K series, and now suppose K shell. Now suppose the electron from L shell occupy this position, then the kind of K series X-ray produced is K alpha. It is called as K alpha. Suppose this vacant position is occupied from the M series X-ray, the M shell. Then at that time you can call this K series X-ray as K beta. Suppose this vacant position is occupied from the electron in N shell, then it will be called as a K gamma, and so on. Similarly for L series also. Suppose the X-ray is L series X-ray, that means the electron from L is displaced and its position is occupied by the outer shell electron M, N, and so on. So suppose the M shell electron occupied the position in L shell, then it will be called as L alpha. Then O shell electron occupied the position in L shell, that will be called as L beta, and so on. So like this nomenclature is actually used to name a particular X-ray, either the X-ray series and the particular photon in that series, just like K alpha, K beta, K gamma, and so on. So this is the X-ray nomenclature, and this is quite simply shown here. So these are the spectral line in different series of characteristic X-ray spectrum. So this will be quite clear to you from this diagram. So suppose this is the first shell, L shell, K shell, n is equal to 1. Second shell, L, n is equal to 2. Then M shell, n is equal to 3. Then n is equal to 4, n shell, and so on up to n is equal to infinity. So whenever the vacant position in K shell is occupied from the electron in L shell, that photon, X-ray photon given out, that is K alpha. Similarly, if this vacant position in K cell, vacant position means which is produced because of the highly energetic electron striking on the target atom, and the electron from K shell has been displaced. Okay, so this if the vacant position is occupied by the electron from M shell, then it will be called as K beta X-ray. Similarly, if it is occupied from N shell, it will be called as K gamma. Now you can see here, the energy difference here is much larger. Therefore, the wavelength of K gamma is smaller than wavelength of K beta. Wavelength of K beta is smaller than wavelength of K alpha, and so on. Similarly, you can think of the L series X-rays. This is one L alpha. You can see here L alpha. So transition from M shell to L shell to occupy the vacant position in L shell. That photon given out will be L alpha. Similarly, transition from N shell to L shell to occupy vacant position in L shell, that is the L beta X-ray photon. And this is the M series, M alpha, M beta, M gamma, and so on. So like this you can understand, once you know the nomenclature, how the spectral lines in different series of characteristic X-ray spectrum are named. So for different series, lambda varies, as you can see here, the K series, L series, and M series. So the energy differences in K series, it is much larger, therefore lambda is much smaller. So lambda for K series is smaller as compared to lambda for L series. So lambda for K is smaller than L, it is smaller than M, and so on. So K series has smallest wavelength, then L series the second smallest, M series the third smallest, and so on. Okay, so lambda for K is smaller than L is smaller than M. This is the representation. Okay, similarly, if you think of the lambda for particular X-ray photon, K alpha, K beta, K gamma in a typical series like K series, then the wavelength varies, as you can see here. For a particular series, for example, here K series, lambda varies as K gamma is smaller than K beta is smaller than K alpha. And this is very obvious because the energy difference is higher. So energy is higher, therefore lambda must be smaller here, smallest. Okay, so that is about the relation among the different photons in terms of their wavelengths and for different series also. Now, if you consider the target material, okay, so X-rays in the same series, for example, K series, produced from an element of higher atomic number. If you consider the element, that means the target element of having higher atomic number. So this X-ray in the same series, that is K series, produced from an element of higher atomic number is less than that produced from an element of lower atomic number. Why this is so? Because this is very obvious. The positive charge in the nuclei is much greater of high atomic number element, target material. So therefore the binding energies are greater there. The K shell binding energy of the higher atomic element will be higher as compared to K shell electron binding energy of low atomic number element, and therefore definitely the wavelength of high atomic number element for the same series as compared to the lower atomic number will be definitely smaller. Okay, so this is how one can compare the wavelength of the particular series of X-rays, uh, the same series of X-rays produced by different elements having different atomic number. And the same study was actually carried out by Mosley. So Mosley's law is an important aspect in the study of X-ray spectra. So what Mosley did, he has studied the X-ray photons, the wavelength of X-ray photons or frequencies of X-ray photons for different target elements, and from his study he has plotted the graphs. Okay, so according to this Mosley's law, the frequency of spectral line in the characteristic X-ray spectrum varies directly as the square of the atomic number of the target element. So the frequency of a particular series and particular characteristic X-ray line in a X-ray spectra is function of the atomic number, square of the atomic number of the target element. So you can say that the frequency of the X-ray photon, of characteristic X-ray photon, is directly proportional to Z minus B bracket square. Okay, so where Z is the atomic number and B is a constant, which is a particular screening constant. Okay, the screening effect due to electron is considered by Mosley, and he has added this constant here in Z. So Z minus B. So B is a screening constant. So you can say that this instead of writing this, you can write it in this fashion also. Square root of nu. Nu is the frequency of the X-ray characteristic X-ray photon. So square root of nu is directly proportional to Z minus B. So Z is the atomic number, B is a nuclear screening constant, and if you consider the first shell, K is equal to 1 or K series X-ray photon, then for that this constant B is equal to 1. Okay, so this graph, Mosley's plot, you can see here. So for example, a typical X-ray photon in K series, that is K alpha, and typical X-ray from K series, that is K beta, they are plotted. So for different elements having different atomic number in an increasing order, you can say that the frequency is linearly increasing. So it is directly proportional to the square of the atomic number. So square root of nu is plotted against the atomic number Z, and you can see these curves are quite a straight line. Now Mosley's law is very important. It has number of applications, and we are going to see now some of the application. Before that, let us see the actual mathematical form of Mosley's law. So the wave in terms of wave number, that means 1 upon lambda, nu bar is wave number. Instead of writing the equation of Mosley's law in terms of frequency, in spectroscopy, you know that this wave number term is most useful to represent the spectral lines. So nu bar is 1 upon lambda, that is equal to R in bracket Z minus sigma square in bracket 1 upon N1 square minus 1 upon N2 square, where R is the Rydberg's constant. Okay, earlier also in Bohr's atomic model, we have seen this Rydberg constant R. It is the same thing here also. Z is the atomic number, then sigma is the correction factor. Okay, so this is the correction factor, and N1 and N2, these are the principal quantum number of the energy levels. Energy levels means the X-ray photon, which is resulted because of the transition between the two energy levels. So those two energy level, for example, K alpha, where the transition is between K shell and L shell. So N is equal to 1, N is equal to 2. So N1, N2 are having value 1 and 2. So like this, you can just have this parameter here. So this is the exact form, mathematical form of Mosley's law. Nu bar, that is wave number, or it is equal to 1 upon lambda, that is equal to R in bracket Z minus sigma square in bracket 1 upon N1 square minus 1 upon N2 square. So this is the mathematical form of Mosley's law. Now we shall discuss the importance of Mosley's law. How Mosley's law is important. So atomic number and not atomic weight, which determines both physical and chemical properties of an element. So from Mosley's observation for different target uh, elements, he has observed the frequencies of X-ray photons, and from his study he found that it is directly proportional to the atomic number. So both the physical properties and chemical properties of an element, they are dependent on atomic number and not atomic weight. So this is the important conclusion. It is proved from this Mosley's law. Then one more important conclusion, that the elements in the periodic table must be arranged by atomic number and not by atomic weight. So this is very clear. The physical property depends on atomic number, so it is quite convenient to arrange the elements with their atomic number and not by atomic weight. Okay, so from the curves actually different elements were discovered. So the study of Mosleys law led to a discovery of new elements like hafnium, atomic number 72, promethium, atomic number 61, technetium, atomic number 43, rhenium, atomic number 75, and so on. So by indication of gaps in Mosleys diagram. So from the Mosleys diagram, uh, once found the gaps, and these gaps indicates presence of certain elements. And from these graphs or diagrams, mostly diagram, these new elements have been discovered. Not only that, the Mosleys law also help in determining the atomic number of rare earth elements. So some element discovered, rare earth element discovered, their position and their atomic number can be found out by Mosleys law, and fixing their position in the periodic table becomes easy because of the Mosleys diagrams. The Mosleys law, one important feature is that is in accordance with Bohr's theory. So just now we have seen the equation, exact mathematical equation of Mosleys law. Okay, wave number nu bar, that is equal to 1 upon lambda, that is equal to r in bracket z minus sigma square. Uh, so that particular formula in bracket 1 upon n1 square minus 1 upon n. This is what we have studied, that is r. And this you can so here see here the frequency of radiation is given by, this is according to Bohr's theory. Okay, so according to Bohr's theory, when an electron jump from n2 to the level n1, the frequency of radiation is given by this formula. This is according to Bohr's formula, and earlier we have seen the Mosleys formula. Okay, so according to Bohr's formula, nu is equal to this. This is actually r. Okay, in bracket 1 upon n1 square minus 1 upon n2 square into z square. So nu is directly proportional to z square. This is what Bohr's theory tells us, and therefore under root of nu is directly proportional to z. But Mosley took into account the screening effect of electrons. Okay, so actual uh, accelerating electron, highly energetic electron, it is going towards the uh, inner shell electron in order to make it free. But meanwhile, the opposing force of the outer shell electron must be considered. That is what the screening effect. So the screening effect of electrons was taken into account by Mosley, which Bohr did not. And therefore, the equation is slightly different. This is Bohr's equation and this is Mosley's law. So under root of nu is directly proportional to z minus b. So only difference is that here the screening constant has been considered. So this is what Mosley's law. So today we have seen here the uh, what we call the importance of Mosley's law. Then we have studied characteristic X-rays, the reason how characteristic X-rays are produced, and the different series of X-rays we have understood in this particular video.